Hello, here is the question number 9. It reads that a wooden plank is floating on a water in a pool. It is tethered to the bottom of the pool by a string attached at midpoint of an edge of its bottom face, which causes it to float with a diagonal of one of its vertical cross section coinciding with the level of surface of water. And this is shown in this figure. We need to find the specific gravity of the wood. So we need to understand the language of this question. It's a good one. So it says this is let's say pool or water, and on this water, this is the wooden plank which is floating, and the thread is here that can be seen clearly. Now this thread is connected with this midpoint. So if you look at like this three-dimensionally, then you'll realize this is going to be midpoint. So thread is connected from this midpoint. Or here it's like this. You can imagine like this. If we consider it like this, so this is the midpoint from where it is connected. Since it's two-dimensional picture, so it has been shown like this. So that's the meaning of this line that says string attached at midpoint of an edge of its bottom face. So this is the bottom face and its edge is this, and but this midpoint it has been attached. Okay. Furthermore, it reads that it is floating with a diagonal of one of its vertical cross section coinciding with the level of surface water. So this is floating in such a manner that means if we cut it, see, so there's going to be a vertical cross section, or we can have a vertical cross section like this. This is a vertical cross section maybe, and if this is a vertical cross section, so this diagonal is horizontal and it is on the level of liquid water. So that's another condition. So these are two conditions are known to us, or informations are given to us. Based on this, we need to find the specific gravity of wood. So after understanding the question, we can solve like this. So we are assuming that tension is T, which is acting at this A point. Again, we are working in 2D stuff, and we are drawing the free body diagram of the plank. Since it is at equilibrium, so forces must be balanced and torques must be balanced. Buoyancy force is FB, and where the buoyancy force is going to act, buoyancy force acts at the center of buoyancy. Center of buoyancy is, let's say, B point. And its total weight is going to act at center of gravity. Center of gravity is going to be at, let's say, C point. Now this line, this dotted line is the level of water. It's a horizontal. It's one of the diagonal, and this is the diagonal of the vertical cross section. Now C must be lying on this diagonal because we know C is the center point and a diagonal passes through the center. B is going to be the center of buoyancy. That means it's going to be center of mass of this portion. So we consider this because water is filled only on this portion. So wherever the center of mass of this portion is going to be, because it's a uniform, so or the water will be displaced uniformly, so you will find the center of buoyancy is going to be at this point. So it has to be center of this triangular wedge, and T is acting at the mid of the bottom edge. You know that. Since it is at equilibrium, so we will say the torque must be 0, so we can balance the torques. Now let's consider this torque about point A. So torque about point A, you will find this FB is trying to rotate like this. That means it's trying to lift this plank off, and mg is going to restore it. So both must be balancing. So torque of mg must be equal to torque of buoyancy. Now from this point, let's say this distance, this diagonal distance is L. So I have assumed the diagonal length to be L. So from A point, you will find the center point will be L by 2 in that horizontal version. So mg will be torque will be of mg is going to be mg into L by 2. What about FB? Buoyancy is torque. So it's going to be vertical, right? So we need to find this distance. That means if we consider next figure, this figure, and this is the diagonal, and this is the side of it. Imagining this to be 90 degree. So we have considered this diagonal to be L, right? And we know the center of mass of this rectangular plate is a dependence on this vertical height. So if you look at this vertical height L, and this center of mass is at a distance L by 3, or if we call it H, so it comes out to be H by 3. So this distance comes out to be H by 3, that means L by 3. So we will say the distance from A is going to be basically L by 3. So buoyancy force is going to be Fb into L by 3. Now this is the result from the center of mass, and whenever we have a rectangular plate, its center of mass is at H by 3 from the base. So we are using that directly over here. If you use this, then it's done. So from here we can find this Fb is going to be equal to 3 by 2 mg. Now Fb will be written as density of water submerged volume. You will find half of the volume will be submerged because it's a diagonal, and upside is there is no water, downside it is inside the water. So half volume is submerged. And here you're going to do density of Planck, total volume into G. Volume and G will get cancelled out. So density of Planck divided by density of water comes out to be 1 by 3. And we know density of Planck divided by density of water is known as relative density or specific gravity of wood. And it's come out to be 1 by 3. Hence 1 by 3 will become our correct response. That's how this C will become our answer. Understood? Thank you.